webcast discusses circular orbits. So Isaac Newton did a famous thought experiment, which is called Isaac's or Newton's cannon, and he thought about firing a cannon, and he thought, well, if I can fire it so that the ball leaves the cannon with a faster speed, it will travel further before it hits the ground. And he kept extending that in his mind and thinking, well, if I could give that cannonball enough velocity, it would actually move all the way around the Earth instead of falling down to the Earth. And if that happens, that projectile is called a satellite because it is in orbit around the Earth and it moves in circles. So let's look at an example of Newton's cannon in work. So here we have, and this is actually his illustration of the Earth with some mountain where the cannon is on top. And I'm going to fire this cannon first with a speed of 2,900 meters per second. It doesn't look like it goes very far. I mean, that's actually a pretty fast speed, but it doesn't nearly make it around the Earth. Let's, get close to doubling that. So here it is at 5,100 meters per second. So I'm going to go a little bit faster. Let's try, 6,800. Wow. So now it has made it about a quarter of the way around the Earth, so I'm going to go even a little faster. Let's try 7,300 meters per second. Okay, I think maybe we're in orbit now. Now this projectile, this cannonball, is going so fast that as it moves around the Earth, it keeps moving in a circle because it is falling toward the center of the Earth because of the force of gravity that's being exerted on it, but it is going so fast that it is able to move around the Earth. The Earth is curved, and so the faster it can go, that means that as it falls, the Earth below it is also curving away. Okay, so a satellite is moving in a circle because there is some type of centripetal force, a center-seeking force that keeps pulling it toward the center of rotation. And in this particular case, we're talking about a satellite in orbit around the Earth, so it's the Earth's gravitational force that is providing that pull, that force that is pulling the satellite toward the center of the Earth all the time. If there were no gravitational force, the satellite would just move in a straight line. As we know from Newton's first law, an object that's moving at a constant velocity, that means a constant speed in a straight line. So a satellite is in continual free fall. The only force acting on the satellite is that attractive force of gravity that is pulling the satellite toward the center of the planet. And so that gravitational force that the planet is exerting on the satellite is the centripetal force that keeps pulling it toward the center and making it move in a circular path. So the satellite is continually falling, and it has to be moving fast enough to fall around the planet and stay in orbit. And so let's think about if we could figure out how fast it needs to move. So the force of gravity, the gravitational force, is the centripetal force in this situation. And so if we set them equal to each other and then replace each force with the way that we could calculate that type of force, we know that the centripetal force is the mass of the object that's moving in a circular path multiplied by the radial acceleration, which is its tangential speed squared divided by the radius of the circular path. Okay, so mv squared over r is, we can substitute that in for the centripetal force. And we've learned from Newton's universal law of gravitation that the way we can calculate a gravitational force is the universal gravitational constant g times the product of the masses and divided by the distance between the centers of the two masses squared. Okay, so we've set those two equations equal, and some of these terms can cancel out. I can divide both sides by the mass of the satellite, the smaller mass, and it goes away. And I can multiply both sides by the orbital radius r, and one of those r's goes away. So I could solve for the tangential speed of the satellite and find that I could calculate it as the square root of g times the mass of the planet divided by the orbital radius. So notice that the m in this equation is the larger mass. It's the mass of the central body, which is typically the planet that the satellite is going around. R is the orbital radius. It's not just the radius of the planet. It's the entire distance from the center of the planet to the center of the satellite. And so I have to add the radius of the planet plus the altitude of the satellite. Notice that in this equation, where we're solving for the tangential speed or the orbital velocity of the satellite, the mass of the satellite has canceled out. And so the mass of the satellite itself is irrelevant for determining this velocity. Okay, so we'll just repeat that because it's very important. The mass of the satellite has no effect on its orbital velocity. The speed of an object in a circular orbit around a body with mass m is only determined by the orbital radius, because the planetary mass and the universal gravitational constant are both constant. Okay? And in a circular orbit, the speed is constant. This satellite is always moving at a constant speed. Now, it is accelerating, right, because the direction is continually changing as it moves back toward the center of the Earth. If the speed changes, then the orbital radius must change, and vice versa. So this equation here, v equal the square root of gm over r, is the required orbital velocity for a satellite. And so if the orbital radius were to get smaller, that means that in order to stay in orbit, the velocity would have to get bigger. Or if we change the speed, let's say that we make the speed smaller, it would mean that in order to stay in orbit, the orbital radius would have to get larger. So they are related through this equation. Okay, let's go work a problem involving a circular orbit. And so I'm in worksheet 7C, and let's talk about the International Space Station. It has a mass of 417,000 kilograms. It orbits the Earth at an average altitude of 362 kilometers. And we're going to assume that its orbit is circular, and we want to find its orbital speed. Okay, so one thing that I'm noticing is that they are giving me an altitude, and so I need to find the orbital radius. And that is going to be the radius of the Earth plus the altitude. And of course, everything needs to be in standard units of meter. So the Earth's radius is 6.38 times 10 to the 6th meters. But they gave me the altitude in kilometers, and so I'm going to convert that to meters, 362,000 meters. Okay, so the orbital radius here of the space station is 6.742 e to the 6th meters. Okay, now let's find the orbital speed. So it's going to be the square root, the universal gravitational constant, times the mass of the central body divided by that orbital radius squared. let me just, actually it's not squared, right? It is just the orbital radius. Okay. Okay, and so we'll plug in here. Got G. Okay, I've got two masses that were given to me, the mass of the space station, which is the satellite, and the mass of the Earth. I want to put the mass of the Earth. Remember that the mass of the satellite is actually irrelevant here. And so I'm going to choose that larger mass, 5.97 e to the 24th kilograms. And then I'm putting in the orbital radius that we calculated. And let's see. So I've got G times 5.97 times 10 to the 24th divided by that orbital radius. And then I need to take the square root of that. And I get 7,685.2 meters per second. That is the speed, the tangential speed of the International Space Station.